On page 132, you have, let's do, hydrogen is easy, right? Hydrogen in its elemental form is just that. No big deal. Okay, we had hydrogen. All right, now we get to oxygen. Thank you, no, I appreciate it. Oxygen, remember, has 6. 1, 2, 3, 4, 5, 6. So I'm going to put the other one over here. 1, 2, 3, 4, 5, 6. Okay, now what we have is we know we can bind these two together, and we can actually bind these two together, can't we? That one's fairly easy. We're not like shifting whole pairs over, are we? And so we've got this, and then, now once you do it, count them. 1, 2, 3, 4, this guy's happy. 1, 2, 3, 4, this guy's happy. Got to do that part, because otherwise, like on that one where we did the carbon monoxide, we wouldn't have seen that we had to shift like that, would we?
So hydrogen is sort of like a metalloid?
No, sir. Hydrogen is a non-metal, period. Nothing else. Hydrogen is a non-metal. Don't ever do anything else with hydrogen. They're very clear on that the hydrogen is a non-metal. It's a non-metal, but it's stuck over here because it gives away one electron when it's getting together with things. So, in other words, it's put over there because of its number of valence electrons. There you go. Okay? Okay. Look at nitrogen. Actually, all of the homonuclear diatomics are gases. That's a good point, Steele. I don't know if I said that. All the homonuclear diatomics are gases. Okay? Okay, let's do nitrogen. Now, nitrogen is in group 5, so it has 5 valence electrons, correct? So we go 1, 2, 3, 4, 5, and this one is 1, 2, 3, 4, 5. Okay, once again, you can really play connect the dots here and just go like this, and like this, can't you? Right? So this one is still fairly simple because you can just play connect the dots. This guy has 4, 1, 2, 3, 4. This one, 1, 2, 3, 4. Okay, it only gets a little dicier when you can't just, for me at least, okay, maybe you guys are sharper, but I like playing connect the dots. And when I can't just play connect the dots, then my brain has to go farther. And then I got to go, okay, where can they share another pair of electrons? But that's not that hard, is it? You just go, okay, we'll just move one of these pairs over here. And this guy that had 4 still has 4, but now the other guy has 4 too, so everybody's happy, right? Jonah?
So everyone has to have 4?
Everybody but hydrogen. Yes, yes, yes. 4 pairs. Remember? Octet rule, right? Everybody wants 4 valence electrons, so everybody's going to go for 4, right? Okay, good. Good question. Excuse me, 4 pairs, 8 electrons. Thank you. Which is 4 pairs. You are absolutely right. They're going for 4 pairs, 8 electrons, and remember that the lines are a pair, so that's why I can count them, because that actually, when I say 4, it actually has 8 electrons around it, doesn't it? At least it thinks so. But this guy thinks so too. So they're really sharing 6 electrons. How tightly bound are they together that they're sharing 6 electrons? Very tightly bound together. Now, remember back when you learned that nitrogen is an inert gas in the atmosphere? Guess why? They share 6 electrons, and they're sitting there going, I don't think we're going to mess with anybody else. You know? So, an inert gas. Okay.
What about sulfur? It's not a metal and you can't get water out of that atomic.
Sure, absolutely. But sulfur, we're not breathing 78% sulfur. We're breathing 78% nitrogen, aren't we? That was my point. You and I didn't have physical science together, but I think most of these people were tortured with physical science. No. Did you take physical science?
A while ago.
Okay, well, you remember that it was 78% nitrogen, 21% oxygen, 1% other. We'll do that in our sleep, right? And that nitrogen is an inert gas, which I told my classes is a couch potato gas. It just goes, just sits there, don't knock me off the couch type of thing. And so that's why. Okay, so that was what I was referring back to in case you didn't have me for physical science. All right, let's see. So we get back to the instructions. We ran through it. We put the one with the most unpaired electrons in the center. We put the other ones around it, and then we start attaching to make paired electrons out of the unpaired ones. And then if that doesn't make everybody have the 4 pairs, then you start moving those pairs in between them. But make sure when you get down that everybody has 4 around them, except for hydrogen, should have 1 pair. So 4 pairs or 1 pair. And so CH2O, did we already do that one? Okay, well, just in case, and then H2O, 2, 3, 4, 5, 6, right? 1, 1, 4, 6. Because that's what groups they're in.
Is that carbon dihydrogen oxide?
Oh, he's not going to ask you to name something like that, but I'd say it would be carbon dihydrogen monoxide. You'd have to put the mono in front of.
Close.
Yeah, okay. But I don't know if that's what this is called, I'll be honest with you. And then we've got a pair here, don't we? Right? And so we go, now we're going to check it. We're not going to just leave it. 1, okay, 1, okay, 1, 2, 3, 4, okay, 1, 2, 3, 4, okay. Check it. Don't just move on because it may not be right. And I'm going to tell you right now, on the other book, the test, there's one that can be done 2 different ways and be right. And the answer key only had 1, and I had a student show me the other way, and I counted them. I go, oh my goodness, you're right. So never give up. Just keep trying until it works. Get your pennies out. Okay. Remember, you can't add electrons. You can't subtract electrons. You have to use what's there.
Unless it's an ion.
All right, but then we're transferring. I'm talking about these guys. These guys, they're just sharing, so you're moving them around. What is the Lewis structure for HC?
Oh, just right here. It says it's called
N.
formaldehyde.
Oh, the last one. Yes, sweetheart. It's called formaldehyde, but that's going to be its common name. And so you and I wouldn't know that, and so we would have to name it the other way. Just like the common name for this is hydrochloric acid, but you're not going to need to know that. So how would you name this?
Hydrogen monochloride.
Good, hydrogen monochloride, right? Hydrogen, because you don't put the mono on the first one, very good. Monochloride. But see, I know that's hydrochloric acid, okay? And when you get to the acid chapter, there's a few acids you're going to have to know because they go by their common names, like the formaldehyde would, but you and I wouldn't necessarily know that. He's a PhD in chemistry. He knows all this stuff, so it's all good. I don't know how he is in the kitchen, but I'm pretty good in the kitchen, so we'll just go with our strengths, right? Okay. So let's see. Did we do that one? We didn't do that one. HCN. Okay. Who has the most unpaired electrons? We have 1, we have 4, and we have 5.
Carbon.
Carbon has the most unpaired. That's good that came up. Oh, think about this for a minute. 1, 2, 3, 4. He's got 4 unpaired. Nitrogen has 1, 2, 3, 4, 5. So he's only got 3 unpaired. Thank you. I'm really glad that came up. Does everybody see that?
Hydrogen would only have 1 unpaired. But it only needs 1 paired.
Okay, right, but he doesn't have the most unpaired.
Exactly.
Okay, so hydrogen has only 1 unpaired, so we're not going to put him in the middle. And I'm going to hook, let's say I put this here, and then I go like this, and like this, and like this, which is really ugly, but anyway. Okay, but let's see if that worked. I have 1, 2, 3 between these 2 guys, and he's still got a pair. I have 1 between these 2 guys, right? This guy's got 1, yay! This guy's got 4, 1, 2, 3, 4. Yay! This guy's got 4, 1, 2, 3, 4. Everybody's happy, except for the person that did it. No, I'm kidding. Okay, all right, you see how that worked? Okay, let's do the next one. So, the comprehension check. What is the Lewis structure for the following? And there's our carbon monoxide and carbon dioxide. Carbon monoxide, so we have 1, 2, 3, 4. Oxygen, 1, 2, 3, 4, 5, 6. Okay. The easy part is connecting the dots, but we only see 2 there. I'm going to make a pair out of these guys. So I'm going to take this one and move it down here, okay?
Now we just need to make
Okay. Right, now we have this. But we are not done. Even though this guy has 4, this guy only has 3. So all we got to do is move this pair between them. That's all we got to do. And we're allowed to. And look now, 1, 2, 3, 4, yay. 1, 2, 3, 4, yay. Right, now I'm just going to make it pretty and balanced and put that over there. But you don't have to.
It doesn't matter.
No. I straighten pictures and close drawers too. Okay, so just, all right. That's the Lewis structure for that one. Now let's do carbon dioxide. So we're going to with 2 of them. We still have carbon in the middle, 2, 3, 4, because it's got the most unpaired electrons. Here we've got an oxygen, 1, 2, 3, 4, 5, 6. And I'm going to put the other one over here, 1, 2, 3, 4, 5, 6. Okay, now let's start connecting the dots. Here we got a pair, here we got a pair, here I have a pair, here I have a pair. I didn't have to do anything fancy on this one, did I? So I go like this. I have 2 pairs here with 2. I have 2 pairs, 2 bonds here with 2 pairs. This would be the Lewis structure on carbon dioxide. It's easier than carbon monoxide because we didn't have to take a pair and just kind of go jamming it in between them. To me, it's easier. To me, it's easier. It might be fine for you because it's the first time you're seeing it and you're going, oh, that's not a big deal. I just move that pair over there. And really, if you think that way, you're great. It's good. Think that way. Okay? I'm a connect the dots person, and so my brain forgets that I can just grab them and move them. So if you do that, you're in good shape. Yes, sir?
What would be dicarbon pentoxide?
Dicarbon pentoxide, right? Okay. I'm not doing it. There is no way. No. Okay. So naming them, we already said with ionic compounds. Now, this is very important. He will do it to you on the test. Did everybody hear me? He will do it to you on the test. He will have a group of things. He goes, name these things, and he will throw an ionic one in there or two. And you'll be cruising along going, di something, mono something, D, and then you get to the ionic one, and you're going to do the same thing. Don't. It'll be wrong. So what is I'm giving you the heads up. So what is the first thing you do when you're naming these compounds? You're going to ask yourself and start getting used to this question because you're going to be asking yourself this a lot. Is it ionic or covalent? Because they act differently. And so you've got to ask yourself that question whenever you're working in chemistry. Is it ionic or covalent? And then if it's ionic, your brain's supposed to take the files on the ionic compounds and shift into those gears. And if it's covalent, you're going to shift into the covalent files in your brain and the covalent gears. Okay? Yes, ma'am?
And if it is ionic, how do they want us to write it?
If it is ionic, you're just going to write, the name is going to be name the first ion, name the second ion with an "ide" ending. You don't have any numbers.
I know what you mean. Okay.
Right. But if it's a covalent compound, then you got to add the numbers.
Because ionic doesn't have the prefixes.
Right, because there's only certain charges they can come up with, and you will balance them, and you're done. Right? Unless you're a metalloid, and then they're going to give it to you in a Roman numeral or say the number. So let's look. It says on the example problem on page 135, example 5.3, it says, what is the name of P2O5? So, Connor, I should get you to do this one. What is this one? That's phosphorus, so what is this one?
Diphosphorus pentoxide?
Good. Diphosphorus pentoxide, and it's pentaoxide. I would have dumped the A when I had the O there, but I want you to notice he's got the A there. Diphosphorus pentaoxide. Isn't that weird?
It says that sometimes it's dropped.
He didn't drop it, did he?
Oh, either's
I would have dropped it. I would have said pentoxide. I'm with you.
Correct.
Okay, so yay, both ways. You got it both ways.
Because we don't have to say,
Because that sounds weird, doesn't it?
Yeah.
Pentaoxide? It should be pentoxide. I mean, in my mind at least, but
but in my mind, that's how things work.
Yeah.
Write the Lewis structure for us.
No, No. You're mean, Tim. Okay, everybody, what is the chemical formula for sulfur trioxide? You tell me. Chemical formula. Sulfur trioxide. How am I going to write it? SO3. Sulfur trioxide. Remember, we don't give it if it's one on the first one. We just ditch it. Okay. Well, we don't ditch it. We just say the name. So, let's try the comprehension check. What is the name of CCl4? So what is the name of this?
Carbon tetrachloride.
Very good. Carbon tetrachloride. So we still do the "ide" ending, don't we? But how do we know this is a covalent compound even though it's got the "ide" ending? How do we know? What's missing in it? There's no metals. Yes. There's no metals, so we know, okay? Also, there was another thing. When we heard the name, there was a tetra in it. Would that be in an ionic compound's name? No, it would not. Okay? So if you only had one chlorine at the end, it would say monochloride, and that mono tells you, doesn't it? It tells you it's a covalent compound because you're not going to have those names in ionic compounds, correct? Are we good? Are we getting this? Okay. The next one, it says the chemical formula for silicone, which is Si, monoxide, silicone monoxide. How do I write that formula? Do I have to do anything to that? No, we're done. Silicone monoxide means there's one of those, so then we're done. Right? Like I said, be ready for him. I'll tell you what, hold your place there and turn to page 159, please. Oh, he doesn't.
Flip right to it.
He doesn't do it there. Where does he ask you to name things? Okay, right there. Number 4 on page 159. Notice he says, name the following molecules. Do you see any ionic compounds in there?
C.
Thank you very much, Christian. C starts with potassium. It is an ionic compound. He's got you clipping along naming these bad boys, and then all of a sudden he throws an ionic one in there to catch you. Don't let him catch you. Make sure you ask yourself, is it ionic or covalent? Look for that metal up front. Okay? Yes.
So, short way to remember, covalent does not have metals, ionic does. Because ionic is going to have.
Right. And there's not a real good short way, because then from there it should open the files in your mind that because it's got a metal, metals want to give an ion, they're going to become positively charged, and then the nonmetal is going to take the electrons, therefore it's going to become negatively charged. There's, that should open those files. Mm-hmm. Whereas with the covalents are going to share. That means that in your mind, okay, shared pairs are covalent bonds, right? And in your mind, that should open up. Everybody's going to try to get to 4 pairs, except for hydrogen, which is only going to come up to 1 pair, and that we're going to name them differently because they can get together more than one way because they're sharing. And because they're sharing, they can get together more than one way. Ionics can't. They can only get together one way because of those charges.
Yeah, I'm trying to get them together.
That's why I'm
very easy to get
right. That's why I'm trying to be very clear. Now remember what I told you: ionics transfer, covalence share, and then that should open up other files in your mind. Well, if they're giving and taking, transferring, somebody's going to end up with a charge, and I know metals will end up with a charge, and non-metals will end up with a negative charge. The metal's positive, the non-metal's negative. You see what I'm saying? So for me, that ionics transfer, covalence share opened up the further information that I needed. I hope it does for you.
The ionic compounds have a charge. Why don't they just push each other away?
Because they have opposite charges. So like sodium chloride, which is table salt.
No, I mean like if you put multiple together, like
They build crystals. That's why we call it salt. They all build crystals. He's saying, why don't they repel each other? Because they actually build on one another. They build crystals. Why? Well, because this one, when it's turned around, and it wouldn't be written this way, but when it's physically turned around, that would attract, wouldn't it? And then another one would be flipped the other way, and another one, and they build huge molecules that are called crystals, and we eat them as salt crystals on popcorn and French fries. Whew. Yes, Connor. Did you have your hand up?
It looks like dicarbon
Okay.
pentoxide doesn't work.
Okay, we're not doing that right now because we have to finish and we've got things to do still, and I'm sorry. On page 136, but that was, sometimes, honey, they don't work. You may be building a Lewis structure on something that doesn't exist. Does that make sense?
That doesn't make sense.
Was it one he gave us?
No. I thought, no.
No, it was one he came up with. See, some molecules don't exist because they don't work. Okay? All right, on page 136, periodic properties and how they affect covalent compounds. And so what he tells us here is that the periodic chart is periodic in that it has certain properties that are true of the ones that are grouped together. Like here, these all have 1 to give away, valence of 1, valence of 2. We already saw how the valence was set up here. Another periodic property is the atomic numbers. Notice they're 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we see that that's a periodic property. They're also done by their atomic masses. If you'll notice, their atomic masses increase like the atomic numbers do as you're going across. Okay, so that's a periodic property. Hang on just a sec. This one here he tells us about is the atomic radius. In other words, we're looking at the size of the atoms. And he tells us here that how we determine the atomic radius is the distance from the center of the nucleus to the valence electrons. Now, this is not, it doesn't work like if I just think about it, okay? I know these guys are bigger than these guys. How do I know that? Well, this guy's got 1 proton and 1 electron, and this guy's got 87 protons and 87 electrons. It's pretty obvious that the size is going to be increasing this way, the atomic radius. But I would think that the atomic radius was also increasing across here, and it's not. It's decreasing, okay? So in other words, the atomic radius increases across the periodic chart this way. This way. Oh, let's go to the second level, which to me is much more telling. So lithium is larger than fluorine. Why? Because as this has, I know, see, this is counterintuitive to me, and that's why I'm trying to make a point to you, because I'd have thought it would go the other way. But what he's saying is that because this one has 9 protons, it holds those electrons closer to it than this guy down here with 3 protons. That the 3 protons just don't have the strength to hold those electrons as closely as the guy with 9 protons, who can hold them tighter. And therefore, this guy's electrons are farther out there than this guy's because it's got more protons to hold them in closer. So the first periodic property that you're supposed to learn is that the atomic radius increases this way, and I would memorize it this way. Okay, he's got that basically. No, well, he's got it decreasing. So if you want to go the other way and say it's decreasing, that's your choice. Personally, I look at it, who's getting bigger. But what he's got is he's got them going the opposite direction, and he says the atomic radius is decreasing. That's true too. It's getting smaller, it's getting smaller. Your choice which way. But I'll tell you what, we are going to be learning other periodic properties, and so it's probably best to just think through it. But anyway, either way, you're going to have to be able to do that. Now, he says this is generally true. He says on page 117 in the little pink box, as you travel up the periodic chart and to the right, the atomic radius increases. And then if you turn the page, he shows you that the electronegativities tend to also be a periodic property. And he says electronegativity is a measure of how strongly atoms attract electrons in a covalent bond. How strong they are to grab the shared electrons. Are you with me? Yeah. That's electronegativity. You can think of them as a negative character because they just don't share as nicely, right? The more electronegative they are, the more they grab it and keep it to themselves. So they're a negative individual. If you want to remember it that way, you can. Or you can remember it that because they're keeping the electrons more of the time, they're more negative because the electrons are negatively charged, aren't they? Okay? Now look at it. He says it on, so as far as periodic properties, and so here he did this decreasing. Let's see if we can use the same arrows. Maybe we'll just keep the arrows going in that direction. With atomic radius, we know this was decreasing. But look at the electronegativity. As the electronegativity is going up, this is increasing. Why? Well, this guy down here has, his electrons are so far out there that he's not really aware of what they're doing particularly. Whereas this guy up here, his electrons are much closer than this guy, so he's going to be closer to the electrons and therefore going to want to grab stuff more. But does lithium really want to grab anybody? No, because he wants to give away an electron. So their electronegativities are really low. But when you get over here, what about these guys? Oh yeah, they want to grab electrons, don't they? Because then they get their 8 on the outside edge. Now let's look at it here then, because we know this guy is going to be a lot more electronegative. He has 7, so he wants it worse than this guy. Okay, he's going to be very electronegative, and he's got the protons to pull that stuff in, right? He's got more protons and all. But this guy down here, even though he's got more atoms, his electrons, protons, not atoms, more protons, his electrons are so far out there that he doesn't have the same pulling capacity. So what we see here is the electronegativity increases this way and increases this way in general. Now look at the chart on page 138. He actually gives you the electronegativities of these guys, and you see that it's not always true. It's an in general statement. Yes, sir.
I found that a lot of the homonuclear diatomic elements had the greater electronegativity.
The ones that make up the homonuclear diatomics.
Yes.
So let's see, hydrogen's pretty high, nitrogen, oxygen. Yeah, look at that. The ones that exist in homonuclear diatomics are the highest. They are the highest electronegativities I see on the chart. In general, yes. Well, they are. They are the highest, aren't they? And that's probably why God made them exist as homonuclear diatomics, because if not, they would be so aggressively trying to grab the other guy's electrons. No, I'm telling you, oxygen is that way. That's why they say that you want to take vitamin C and things that are antioxidants. Listen to the word. Free oxygen radicals destroy you. It's like rusting on the inside of your body. Because what is rust? Rust is where oxygen attacks iron, right? And it corrodes it by making a bond with it and corroding it. And it happens in our bodies too. So we're supposed to take antioxidants so that those oxygens aren't free to run around and try to grab hold of everybody else. And why would it do that? Because it's very aggressive because of this high electronegativity. Thank you for that observation. That's good. So remember, as you travel, we got a pink thing here. As you travel up the periodic chart and to the right, the electronegativities increase. Now, electronegativity, how strong it grabs to try to grab the shared pairs of electrons. At the bottom of the page, it tells us that polar covalent molecules excuse me, have uneven sharing. And if you had me for physical science, you've heard that before. I told you to memorize that forever ago. Polar covalent molecules are unevenly shared electrons, and therefore, because of the uneven sharing of the electrons, they end up having a slight charge over the molecule. On page 139, the comprehension check, you were supposed to order these depending on from the lowest to highest of the atomic radii. Hopefully you did that. You remember that the atomic radius is decreasing this way. So going from lowest to highest, it would have been bromine, astenine, so Br, As, Ga, Sc, and K. How's that? That makes it easy. And then the electronegativity from lowest to highest, you should have ordered it At, I, Br, Cl, F. Okay, now let's get to this experiment. We're going to try to do this experiment, and we're going to try to do it without a sink, so that should be interesting. But we're going to try to do this. I come over here with my little table.
What made low like fluorine, which is very electronegative, and something else that isn't very electronegative formed together, it would become
A polar molecule, like water's a polar molecule. Oxygen is more electronegative than hydrogen, quite a bit more, and so it keeps the electrons around it more of the time, right? We're going to try this and see. And I'm going to start with water because then we'll see if this is working at all. How's that? Rather than using a funnel, we are using a cup. And we've got a nice, I'm going to see if a comb works. I had a student tell me the comb works better than the balloon. And I have gel in my hair, so it may not work. Oh, did you see it coming over? Slightly. We need a balloon? I happen to have balloons. And then, Tim, I'm going to get you to hold the thing while I do the balloon, but I'm going to use your head, all right? Well, I'm going to have to. Hang on, sweetie. Hang on. Well, I'm going to try to grab his electrons. We'll see if it works. Let's see. Hang on just a sec. I'm going to try to pour this in here. Okay, hold that up there. You got to hold it up shoulder height is what he said. So, and let's make it actually go in there. Okay. Oops, sorry. Nope, you're okay. It's just water. Okay, I'm going to try to grab your electrons. Okay?
it's poison, not water.
Oh, there you go.
Do you see it move? Okay, I'm going to.
I do.
It's not wet, sweetie.
Oh my.
Okay, did everybody see it?
Now I saw it.
Did everybody see it? Did you see it?
Yeah.
Jess, yes? Okay, dump that in, sweetie. Now we're going to do oil. Just dump it in.
Oh boy.
Oh, and you know what? Just so that, no, don't leave. We're not done yet.
What is the formula of oil? Probably something big.
Yes, probably something big. Okay, you're going to stand back here again because they need to be able to see too. Make sure that it goes in here, okay?
Okay.
Okay, we're going to do this. I hate this part. We're going to do this with oil. Okay? We're going to do the electrons. Do we see
Oh, it's
anything?
pushing.
Oh, that's just coming through, but it's not actually, that's funny. I've had somebody say that before. They thought it pushed.
It is pushing, I think.
I don't think so. I think it's just kind of coming through in glops. Okay. Did anybody see real movement? No? Okay.
Either way, you can.
Yeah, it could. You want to try one more time? See, it doesn't.
Oh, it pulls a little bit.
Okay, he said if you get a slight pull, it's impurities in it, because you shouldn't get pulling. Everybody give a hand to Tim. Yay, Tim. Clap for Tim. Thank you, Tim.
Good job, Tim.
Okay, we'll get that over there. Okay. So the comb didn't work. Bummer. My student, I had a student that sent it to me on his phone, and he did it with the comb, and he did it with the sink,
Yeah.
and then he took the comb and went like this, and the water literally made a right angle. I'm telling you, man, the water just woo, and I got it on my phone. He sent it to me, and I'm like, wow. What you see, and it shows you on page 141, is that these are polar covalent molecules. They have a slight charge over them. The oxygen is more electronegative than the hydrogen, and therefore the oxygen has a slightly negative charge, not a real charge, and the hydrogen end has a slightly positive charge. That means fractional, the delta, small letter to Greek letter D, okay, delta, and it means fractional. And so we see that polar molecules have uneven sharing of electrons, and therefore there's a slight charge over the molecule. And on page 191, it shows you why the stream of water will move towards the electrons on the balloon, because they have a positive end, slightly positive, slightly negative end. The slightly positive end would reach towards the electrons. If we had been able to charge the balloon or the comb with a positive charge, it would have just flipped around and the negative end would have gone towards it. So it would have still moved towards it, because polar covalent compounds are attracted to other charged particles. So other charged particles would be other polar covalent compounds or ionic compounds. Now the oil just kind of goes, unless it might sputter, because there might be impurities of water in it that are attracted. But otherwise it should just go straight down, because, turn to page 142, please. Those are purely covalent bonds. They are equal sharing in them, and therefore they don't have that charge to be grabbed hold of. And so when they have evenly shared electrons, they're purely covalent compounds. And so at the bottom of the page, I'll tell you what we're going to do is we will do these two Lewis structures. Oh, let's do them real quickly, then we can be actually where we are. So we have NF3. So we have N, which is 1, 2, 3, 4, 5. F, 1, 2, 3, 4, 5, 6, 7. F, 1, 2, 3, 4, 5, 6, 7. Number 8 says construct a Lewis structure for NF3. 1, 2, 3, 4, 5, 6, 7. We get pairs here. Okay, there's our Lewis structure. And then it says, does it have polar covalent bonds? Yes, because fluorine is definitely more electronegative than nitrogen, isn't it? And so those polar covalent bonds, it would be pulling more in that direction, wouldn't it? Okay, so there's uneven sharing. It says, where is the slight positive charge and where's the slight negative charge? These guys would be slightly negative, right? The F's, and this guy would be slightly positive. He would lose the electrons more of the time.
You said that was because why again?
Because the nitrogen is to the left of the fluorine. Remember, it increases this way and this way, okay? And then the next one says the electronegativity of sulfur is 2.5, the electronegativity of chlorine is 3.0, and the electronegativity of iodine is 2.5. Which combinations of any two of these elements would produce a polar covalent bond? So a polar covalent would be uneven sharing. So if we had S with chlorine, sulfur with chlorine, or the iodine with the chlorine, either one of those would be polar, wouldn't they? But you could not put the iodine with the sulfur because they are both 2.5, which means that if you put those two together, you would actually have a non-polar molecule, a purely covalent molecule. Does everybody see how that works? Okay, that's where we were supposed to get up to today. You doing okay? All right. Have a blessed week.